On September 24, 2025, a SpaceX Falcon 9 rocket roared to life and lifted off from Kennedy Space Center in Florida, carrying a trio of scientific missions designed to push the boundaries of our knowledge about the Sun, the Earth, and even the very edge of our solar system. The rocket's payload included NASA's Interstellar Mapping and Acceleration Probe, or IMAP, the Carruthers Geocorona Observatory, and NOAA's Space Weather Follow-on Observatory, also known as SWFOL-1. Together, these spacecraft are headed toward a remarkable location in space, about 1.5 million kilometers away from Earth, known as the first Lagrange point. At this unique gravitational balance point between the Earth and the Sun, satellites can hover in a stable position, maintaining a constant view of the Sun without being pulled away by Earth's orbit. It is the perfect place for missions that need to study solar activity and the way space interacts with our planet. The centerpiece of this launch is IMAP. This mission will travel to Lagrange Point 1 with the ambitious goal of mapping the boundary of our solar system's protective bubble, the heliosphere. The heliosphere is created by the constant outflow of charged particles from the Sun, known as the solar wind. These particles form an invisible shield that surrounds our solar system, protecting us from the harshest cosmic radiation that originates beyond the Milky Way. But the exact shape and behavior of this shield are still mysterious. Where does the heliosphere end? How do particles get accelerated to near light speeds? IMAP is equipped with 10 different scientific instruments designed to capture high-energy particles, measure their properties, and trace them back to their origins. By building this map, IMAP will give us a detailed understanding of how our solar system interacts with the interstellar medium. The answers it provides will not only deepen our scientific knowledge but also have practical applications, helping us predict radiation hazards for astronauts who will travel far from Earth. Flying alongside IMAP is the Carruthers Geocorona Observatory, named after the pioneering scientist George Carruthers, who made groundbreaking contributions to ultraviolet astronomy. This mission has a more Earth-focused objective: to study the outermost layer of Earth's atmosphere, called the exosphere, and the geocorona, a giant halo of hydrogen atoms that surrounds our planet. Many people are surprised to learn that Earth's atmosphere does not end at a sharp boundary. Instead, it thins gradually, stretching hundreds of thousands of kilometers into space. The Carruthers Observatory will observe ultraviolet light emitted by hydrogen atoms to build a clearer picture of how the geocorona behaves. This is important not only for understanding Earth's atmosphere but also for interpreting signals from exoplanets, since distant telescopes often detect hydrogen around other worlds. By understanding our own geocorona better, we can improve our models of how planets evolve and interact with their stars. The third payload on today's mission is NOAA's SWFOL-1, or Space Weather Follow-on Observatory. While it may not sound as exotic as exploring the edge of the solar system, its mission is critically important for life here on Earth. Space weather, driven by eruptions on the Sun such as solar flares and coronal mass ejections, can send waves of charged particles crashing into Earth's magnetic field. These storms can disrupt GPS signals, damage satellites, affect radio communication, and even overload electrical power grids. In 1989, a powerful solar storm caused a blackout in Quebec, leaving millions of people without power. In today's world, where satellites control navigation, banking, communication, and national defense, the stakes are even higher. SWFOL-1 will continuously monitor the solar wind, magnetic fields, and energetic particles streaming from the Sun, giving forecasters the data they need to provide early warnings. It will be our first line of defense against space weather. The Falcon 9 launch itself was another milestone in reusable rocketry. After carrying the payload toward orbit, the rocket's first stage returned to Earth and executed a precise landing on SpaceX's facility at Cape Canaveral. This ability to reuse boosters dramatically lowers the cost of spaceflight and allows missions like IMAP, Carruthers, and SWFOL-1 to become reality. Just 2 decades ago, such a trio of spacecraft would have required multiple launches at enormous expense. Today, it is becoming routine, thanks to advancements in both science and engineering. Beyond the technical details, what makes this mission so inspiring is the way it combines different scientific goals into one journey. IMAP will expand our understanding of the solar system's frontier, Carruthers will reveal secrets about our planet's hidden atmospheric halo, and SWFOL-1 will protect modern society from the invisible storms of space. Together, they remind us that space exploration is not just about distant galaxies, it is about understanding the environment we live in, from the Earth's atmosphere to the boundary of interstellar space. Each discovery will connect back to our daily lives, influencing everything from astronaut safety to protecting the power grid here on Earth. As the Falcon 9 disappeared into the sky, it carried not just 3 spacecraft, but also our curiosity and determination to explore. These missions will operate for years, sending back data that will keep scientists busy for decades. They are the latest chapter in humanity's ongoing story of discovery, proving once again that even in the vastness of space, our search for knowledge is unstoppable. With every launch, we push the horizon a little further, and with every mission, we take another step toward understanding our place in the universe.